So, writing GPU shaders in plain Rust, because honestly, most other alternative shader languages kind of suck. So who am I? Well, I got online as Firestar99. I'm a graphics programmer, right? I just make stuff that runs on GPUs and make GPUs go hot. And then sometime during like 2022, I just started playing around with Rust, and then I found this cute little project called Rust GPU. And then I wrote my master thesis. So I'm going to write my master thesis. Okay, I want to use Rust GPU. That thing is cool. I ended up needing a few more features from Rust GPU. So what do you do? Well, you start modding the compiler, of course. That's what you do. At some point, you're getting asked, you've made a few PRs. Don't you want to maintain this thing? We need a few more maintainers. And suddenly, now I ended up actually working commercially for building on Rust GPU and hacking away at it and trying to get it to a better future. So I guess I'm compilative now and not a graphics programmer anymore. So to give you some context of like what Rust GPU really is, first we need to talk a bit about like what are shaders. So basically, shaders are these small little programs, air quotes small, that we run on the GPU. So you can imagine them like for example, there's different types. One of the types, for example, a fragment shader, which is basically like if you're doing 3D graphics and you're rasterizing a bunny, for example, you can imagine like for every pixel of that bunny, this function is getting called, and you basically just effectively return the color of the pixel. So I could just, return orange for the entire bunny, and you'll see an orange bunny. I could, of course, return pink for the bunny, and then the entire bunny is pink. Now that's kind of boring. So of course you want to use some sort of like input variables. For example, the model could have some normals defined, which are basically like defining the surface of the bunny, which direction is up. That's the normal. And if you just visualize that, it looks like this. And now you have a way more colorful bunny with some actual features you can recognize. And you can use this sort of information to do some very basic math in the shader to just get some really, really basic lighting. Like this is a dot product from vector mathematics, and you already have like decently lit bunny, even if it's kind of basic. So so there's also like different kinds of shaders you have. There's a whole bunch of them, but I can't cover all of them right now. The other one that's sort of interesting, like you don't always just want to do like render a model and just compute the color of a single pixel. You want to do all kinds of different stuff on GPUs. So eventually someone got the idea, hey, let's generalize that, and they introduced compute shaders, which you can imagine like you define some sort of grid, like a 3D grid, and for each cell in this grid you call the function. And then within the function you can do whatever you want. You can do arbitrary memory reads, writes, computations, whatever you want. So pretty much if you can, so pretty much like you compile down those shaders and you can just do whatever you want with it, yeah. So generally, how do you write shaders? Well, usually you have something called a shader language, which could be glsl, which could be wgsl, which could be bevy, wgsl, which is like bevy's variant of wgsl, whatever. And what we do is we basically have a shader compiler that takes these shader languages and turns them into what you could generalize as shader IRs. IRs being intermediate representations, so like some sort of specification of how the some bytecode has to look like. For example, there's SPIR-V, which is like a really popular one for Vulkan and stuff, and there's, in a way, also wgsl source code. For reasons that source code, I don't know. And then at runtime, you take these IRs and you pass them to your graphics API. So, for example, Vulkan or wgpu. Now, as this talk's going on, you of course could already reason I'm a Rustoian. I don't want to write these in these very special shader programming languages, which most of the time they look like C. They're more like domain-specific languages, which look like C, but they don't have anything with regards to pointers and stuff. So like pointers without C, that's how they look like. I don't want to write them in that. I want to write them in Rust. And what Rust GPU basically is you take Rust as the input shader language, we turn it into SPIR-V, And since SPIR-V is well spec'd, you could just take that SPIR-V and pass it to Vulkan, and then off you go. You can write your shaders in Rust, basically. Now, of course, not everyone wants to do the Vulkan part, because Vulkan is a rather complicated API to work with. A lot of people also want to work with wgpu, which requires wgsl. So in practice, while we use SPIR-V internally, we can also turn it into wgsl and whatever else you could think of pretty much from SPIR-V, and then you just go off to whatever API you want to have. TLDR, I want you to write your shaders in Rust. I mean, if you're already writing your CPU code in Rust, it makes sense, right? So how does this sort of integrate into the entire system, basically? Well, usually you have, of course, you have migrate, which is, I don't know, some random binary, your application, which opens a window, just the graphics API calls, your game, whatever it is. Like, this is the standard stuff. Now, Rust GPU setup is not as trivial. What you generally see is that you don't have just one crate, you have two crates. And the other crate is a no standard library crate, which we'll go into some detail later. And that one contains all like the shader entry points. So like all your shaders are over there. And the amazing thing is, well, those are two crates, they're both written in Rust. So like what you can just do is you can just add a dependency, as simple as it is, from your main crate to your shader crate, and you can put all your shared data structures in the shader crate. And you could just access them. It's nothing special, which is so simple to do once you write both of them in Rust and don't have to deal with like two different languages and trying to move data around between them. So how would you build that? Well, at some point you're going to start with a Kahu run, a Kahu build something, which is of course going to build your main crate, which of course has to build your shader crate. But that builds your shader crate for the CPU, right? How do we build the actual shaders into SPIR-V blobs you can pass? The typical approach is you have a builder script in your main crate, which is basically like Rust's going to call that to, and you can just do arbitrary whatever you want to just pre-process things. That one, you just basically just call it to a library, which is called cargo GPU install. And cargo GPU install will do a whole bunch of stuff in the background, like, because we're a CodeGen backend. So we call ordinary Rust C, and then basically at the end we just fork out the data stream and do a lot of custom stuff to get it down to SPIR-V. So what cargo GPU install has to do, it has to look up like which version of Rust GPU do you want to use, which is based on our standard library. It has to figure out, okay, it has to download our CodeGen backend. It has to then figure out what kind of Rust C, exact Rust C nightly version our CodeGen backend is built against, or should be built against. Then it has to download the Rust C version, the exact one. Then it has to build the CodeGen backend. And after all of that chaos, it just calls cargo with the correct nightly version, with the CodeGen backend, with a SPIR-V target. And basically just builds the crate a second time for the SPIR-V target. And then once it's built for SPIR-V, you're just getting passed back basically, here's all the SPIR-V files, and you can just do whatever you want with them, basically. Now, why would we want to have both of them in Rust? Well, because what you get a lot in graphics programming, which is probably the most annoying error, is just API mismatches. What I mean with that is, like, if you have to share types between C and Rust, like you see the struct in C, and most of you who have done anything in Rust will probably be able to like write the struct in Rust, right? It's most of the time it's just a one-to-one copy. You change a few things around, you different data types, but they are effectively the same, and you just slap wrapper C on top. Now, to verify that this is actually like the correct, like the API is compatible and you're not getting anything like different offsets, you can, as a verification, of course, just go ahead and compare the size-offs to make sure they are about correct. Now, this is not sufficient to actually check it, but this is a good indicator that it's probably correct. Let's do the same thing with wgsl. And because like most people in Rust are going to be like, of course I write my shaders in wgsl. Have you actually ever attempted to do this correctly? Because it's a mess. Well, of course you can do the same size of here, and you will actually figure out it's 32. Also, I should mention, like, wgsl doesn't even have a built-in called sizeof. So you can't actually assert this ever, but you have to use an external tool to evaluate the size of this thing. So how does wgsl end up with this mess? Well, the answer is pretty much in the vec3. Well, it sounds like it's a vec of 3 floats, but it's actually not. wgsl uses something called the STD430 layout. So graphics programmers, for some reason, don't have something called rep-c. They have a few different ones. The default one you see everywhere is basically STD430, and it has a really funny definition of a vec3, which is it has a size of 12 and an alignment of 16. And if you do the math, that will actually line up with the 32. Well, so like your first intuition would be, why don't we just introduce repr STD430? Well, the reason is simple, we actually can't, because this layout right there is completely illegal in both Rust and C. Because the definition of a layout is, hey, your size must be a multiple of your alignment. That's not the case here. So like the general solution, how do you fix this, is basically, well, just use a vec4. That's literally what all of graphics does. You just don't bother with vec3s, they're a mess. Just use vec4s and waste some space, or combine some fields into two fields into a single field if you want to be fancy. It's a mess, right? So how does Rust GPU do that? Well, we do something really stupidly simple. We just go to Rust C and ask it, hey, what's the layout of this type? Sure, I'm going to use that. So there are no like STD430 or STD140 or scalar layouts, which is graphic stuff. It just doesn't exist. We just copy whatever Rust C gives us, which means if you have a type that is rep-c, that type will have the same layout on both ends. Now, of course, some caveats apply, like if you use usize, which may be different between machines, or like pointers are kind of weird, but it's sort of like the same thing, like you wouldn't send a usize over the wire, over networking, like, yeah, that's silly. And it's similarly here, it's sort of like the same logic applies. This is a different machine, remember that, so don't use usize, use u32 directly, whatever, and it works out. Now, unfortunately, you can't use rep-rust. And for a really simple reason, according to the specification, rep-rust is allowed to change between compiler invocations. At least that's what spec compiles. And that's amazing because they can just change how the representation does its thing, does its layouting, and maybe there's some more optimal way to layout stuff. But for us, it's of course super annoying because we compile things twice. So we need a consistent layout. Which also means there's like this initiative going on called rep-crabby, which is an amazing name to name an API layout engine, which basically guarantees us, hey, we're going to get stable layout across compilers like C, but at the same time, we'll get a lot of the like Rust optimizations. It is not even, I don't even think it is unlikely yet, but it is coming and it would be really interesting for us. And also, like the other thing is, because rep-c does not support things like enums with data inside them, like option or niches, and all that stuff would also be sort of very crabby. Whereas right now we effectively rely on UB if you want to use these types, and even these types have a lot of problems in other ways. Because functionally, the rep-rust doesn't change a whole lot. So like, how do you, now that we can compile everything down, like how do we represent things which we have in SPIR-V and Rust? How do these map to each other? And well, first of all, SPIR-V, it has no operating system. And I mean, Rust is pretty good at the story. Like Rust has a really big embedded systems category, and they all work with no standard library. So amazing, we can just reuse that functionality, be like, hey, we don't want to use a standard library, and it works. Well, SPIR-V goes a little further than that. You also get no allocator. Allocators on GPUs by default are not really a thing. So you get no crate alloc, which you see a lot of crates advertising like, I'm no CD compatible, but I need alloc. Well, those also won't work. So you also get no vec, no hash map, or sort of like data containers. Also, SPIR-V really at its heart is like a register architecture without a stack. So you also don't get any recursion. Just doesn't work on the platform. Everything is type memory, which is, for compilers, that's like a certain type of hell. where everything is, so we have to do like some weird transformation from untyped to type memory, which I'm not going to go into because it'll take forever. And also like SPIR-V has like really weird pointers. Like I said, normal shading languages don't really have pointers for a reason. Well, what it really comes down to, like shaders are really just procedural math programs. They're really just built for number crunching. They're not really built just like a arbitrary general purpose programming language to run shaders with. Right? So if you want to support more Rust, the only real option we have is emulation. Just try to emulate as many features as we can inside the compiler. But like, there's probably going to be some people in the audience which ask themselves, well, doesn't LLVM have a SPIR-V target? And you would be correct. LLVM does have a SPIR-V target. And we need to talk about the different SPIR-V flavors. Because there's one flavor which is basically Vulkan shaders. Like, this is what supports graphics and compute, and you're using it, your games are using it, your desktop's using it, your Chromium even has like a Vulkan variant. Like, literally everything you use on your desktop is somehow involved in Vulkan, or at least OpenGL, which is also not far away from that. So it also means like every single device pretty much has a driver. It's ubiquitous everywhere, and it's well tested. And you can also do fun stuff like transpiling to wgsl if you really need to target the web, because we love standards. And there's the other side, which is OpenCL kernels, which are for compute only. They don't support graphics at all. They're primarily built for like high-performance compute simulations. You can also run that stuff on Vulkan, like whatever. You also need to install the driver separately. And need to figure out how to even install that, which can be a lot of fun. So like, obviously, so LLVM and Zig as well do target SPIR-V, but they target SPIR-V with like the OpenCL kernel variant. And what we try to do is target Vulkan shaders, which is quite a bit different. Now you may be like, why is LLVM doing this silly thing and targeting OpenCL kernels, not just shaders? Well, there's a really simple reason for it. They get physical pointers. With address spaces, which is a whole another mess that Rust also doesn't expose to the user, so that's also not really a great option for us. Whereas in Vulkan shaders, you get fake logical pointers, which are a way bigger mess to deal with and way more annoying. So what do I mean with logical pointers? Well, if you read in the SPIR-V spec, it literally just says 2 sentences really on what the logical addressing model is, which basically means that pointers are an abstract thing, and they don't really have like a physical size or a numeric value. They're really just like aliases, I feel like, in sort of way. And you can only create them really from like existing objects you can alias to, and you can't really store them in other objects, and there's a whole bunch of like weird limitations around them. So like TLDR, you can't do pointer arithmetic. And now think about how much depends on pointer arithmetic in your code. Like, you can't slice slices because that's pointer arithmetic. You're offsetting the slice, the base pointer. You can't have enums of values because the first field in this enum is like the enum tag, and then the remaining fields come after that. So that's also an offset. You can't use any of the core pointer API, which is like such an internal piece of Rust, which is everywhere. Like, you can't iterate a slice because it's using the pointer API to iterate over a slice. You also can't create references to struct members because that's also, of course, an offset. And another additional, like, super annoying limitation is you can't pass pointers as function arguments. That's simply illegal in SPIR-V Vulkan. So, like, the only real thing you can do with logical pointers is you can do array indexing, and that's it. That's like the only big use case of them. So like like the most annoying limitation you'll see is basically you can't, like, not being able to pass pointers as arguments is super annoying in Rust, because reference self is passing by reference, right? So that's a pointer. So how do we deal with, so this is like the most annoying part probably, and how do we deal with this right now? And so we have a certain weird algorithm on current main, which helps with the whole reference self and reference mute self, and it does something really, really simple. If you pass a pointer to a function, we just inline the function. Because if the function is inlined, I'm not passing the pointer to a function, right? So we just work around the rule that way. Now, the problem is that this is not trivial to implement, because at CodeGen time, right, there's a whole bunch of CodeGen units, and they know there are functions, and you can call functions, and they know you know your own function, basically. And you just know there's foreign functions, and you call them, and they may be in your CodeGen unit, they may be in a different CodeGen unit, you may have access to them, you may not. So we can't really do inlining during CodeGen, right? And now the thing is, after CodeGen, we need a linker to link all the CodeGen units together. Now, there isn't really an off-the-shelf SPIR-V linker out there. Or, well, officially there's one in the SPIR-V tools, but that has the to-do is still not stable tag and hasn't been worked on for like literally 10 years. So we need a custom SPIR-V linker. Now, if we have a custom SPIR-V linker, we can do whatever the fuck we want. So what we do is basically we just append something we call the post-link legalization, which is a fancy name of basically being like, hey, I don't care what we emit at CodeGen. We can emit some SPIR-V crap, which is totally illegal, and who cares, as long as the posting legalization cleans it up. So what we basically do is, well, we emit everything at CodeGen time as usual with references as they are legal, and post-link should just do the inlining for us. And at that point, we know the entire shader code. We know everything, because shaders don't have such a thing like dynamic linking or like at runtime and stuff like that. Just doesn't exist. Like, we literally have a closed world assumption, so we can just do whatever we want. And this post-link legalization is a really useful tool, and we're going to use a lot of it. So doing this is fine, but this doesn't fix it for all the pointers. So there's been a research project going on by a colleague of mine for like 2 years or something like this, to try to get a lot more of the pointer semantics in Rust just working natively. But of course we don't have real pointers, so we need some sort of emulation, which is what we call our Q-pointer, our quasi-pointer emulation. And how it works is surprisingly interesting. Like, if we take a look at this sample of a source code, like, what do you see? You have an if on some condition doesn't matter, and either we take a reference to a buffer or we take a reference to a constant, and then we access it. Like in this case, we absolutely passing pointers around, and we only got rid of these pointers, right? So the first thing we do is we just copy the control flow, because it doesn't change. And then for the pointer path, what we basically do is, well, we just use pointer tagging. So we have a tag for a buffer at offset 42, and then for the constant, we have a tag for the constant at offset 0. And once we access the pointer, well, it's basically just we mesh on the tag itself. And if we notice on pointer access, hey, this is a buffer, then we just load from the buffer at whatever offset it is at. And if it's a constant, we just look at our array of constants and just load whatever offset is not there. The amazing thing, of course, is, hey, on the right side, all the pointers are gone. So this is totally, the right side is totally legal SPIR-V logical addressing. So we can just use that. Effectively, what you're seeing here is often also sometimes also described as like generic address space emulation. So if you remember back to like the OpenCL kernel slide, and we're talking about, hey, you need to expose address spaces. If you want to not expose address spaces, you'd effectively do the same thing. So there's like not really an advantage to targeting OpenCL anymore for us. So the other interesting part is, right, what if we change the else branch? And we say, hey, we want to take a reference to the buffer at offset 42 or at offset 17, right? Then if you look at the right side and we just simplify it down, we can, well, look at the tag. The tag is always going to be tag buffer and never tag constant. So the first thing we can do is you can just eliminate all the other branches, set them to unreachable because they are unreachable. And then we look at the match statement and we're like, hey, it only has one tag left, like one case left. So we can just eliminate the match statement. And now, well, is it that different, the code? It's pretty much the same code, right? It shouldn't be that much more inefficient or something. So like if you just do const propagation and range analysis and be a bit smart about how you make this, you can just get just as much efficiency if you don't like mix address spaces. And this is actually good enough to get alloc on the GPU. Because this stuff is surprisingly interesting. So what you do is basically, well, you do the thing I told you at the beginning you can't do. Well, you do extend create alloc, and you're like, hey, I want alloc, and you do your custom global allocator, which in our case, I'm just going to use some random bump allocator into a buffer. You can't use, like, there's no system allocator. You just have to do your own one. But then we can like have an entry point right there, and we can just say, hey, I want to have a vec of 1 to 3. And this bump allocator we've specifically built to just for demo purposes. Well, first, Q-pointer works with alloc, yeah. Now, yeah, oh yeah, I have to mention it really quickly. Like, this is less useful than you think it is, and you'll see later. Basically, you can allocate stuff, but you can't send those allocations to the CPU. That's just not really a thing you can do right now. It's basically just a demo of like Q-pointer is good enough so that you can even use alloc. So like what you can do is basically we can dump, our bump allocator can just dump the allocations that have been done, so I can visualize them for you. And of course you see a vec of 1 to 3 in memory gives me also 1 to 3. What a surprise. Now if we push a 4 into this vec, now this vec has a capacity of 3, right? So it needs to do a new allocation, and then it doubles its capacity, and then it puts the 4 in there, and the other ones are just left uninitialized, aka 0 in this case, because it's a 0 dot buffer. So pushing even works. Now, where it gets really interesting is, what if we take our vec and put it in a box? Because if you look at the values right there, right, you can pretty much assume most of them. Like 6 is probably the capacity, 4 is the length, but what is the thing in the middle? I mean, it has to be the pointer, right? But how do you represent a pointer in memory now, since we have this tagging scheme? So, yeah, this is sort of a really interesting issue, because effectively, our pointers have a tag and an offset. And the offset, of course, needs to be usize, and the tag needs to has some bits. Could be usize, could be something else in this case. But also, Rust-C assumes that the size of your pointer is usize. So like you can see the problem. Effectively, to solve this, tag has to be 0 bits size, ZST type, right? This doesn't work out. So like, where do we store the tag in this case? Well, there's a few options you have, and what we do right now is effectively pointer tagging. So we take the top bits of the pointer and just use it to store the tag. This reduces the addressable range, which you may think, sure, whatever, 64-bit is no huge deal. The problem is, usize is 32 in our platform. And actually, usize doesn't make any sense, because no shader language has usize, because it has no pointers, right? In our case, it's 32-bit. Why is it 32-bit? Well, 64-bit is an opt-in on most platforms. You have to have hardware support for 64-bit arithmetics. And if you want to deploy to like wgsl on wgpu, so you can deploy to your game to the web page, well, wgpu API doesn't support 64-bit at all. So that's like really annoying, and you can't really do much about this, right? So what this effectively means is, while buffers in most graphics APIs currently have a limit of 4 gigabytes, we may have to cut down from 4 gigabytes, which, like, this hurts. Cutting down from 4 gigabytes to, I don't know, and you need a few bits, so it's like cutting down to like 1 gigabyte or 512 megabytes max buffer sizes just to make this work, which is like, that's a really big limitation, probably a no-go for most people. So like, there's a few other options we have. So has anyone heard of the Cherry platform? Few people. So if you've never heard of Cherry, what Cherry basically is, imagine like a RISC processor that has a pointer that is double its size. And the first part is your standard pointer, you know, your address thing. And the second part is basically extra metadata information to validate that any pointer access is in bounds. And this validation happens in hardware. But that means that basically every compiler needs to support this thing where usize is 64-bit and your pointer is 128-bit in order to put all these validation checks in place. So Rust-C actually has, it's like Cherry maintained, or specifically Cherry IoT actually maintain a Rust-C fork where they started implementing all of these semantics, and they have it supposedly up and running, and some of that has been upstream. Could potentially be interesting for us as well. The other option is to just say, we do U64 everything and have 64-bit pointers, and we add emulation down to like 2 U32 operations, which sounds fine. And for SPIR-V, that is fine. Like, there is an instruction called op-I-add carry or whatever it is, and you can do the add operation with the carry included and everything, and then you get to wgpu and wgsl and figure out, well, they don't. So it's sort of like falling into the same trap. The other thing you could do is you could limit pointers to local variables, and that you may never put a pointer into memory. And as long as you put it in local variables, we can just be like, hey, this you need 1 register and you need 2 registers, fine. I just give you 2 registers, whatever. That's not a problem. But I want to leave you with one more thing we've been experimenting around with, and there's this tiny fun library called tinywasm, which is a tiny embeddable WASM interpreter. And we were, because we were thinking about like how do we stress test the system? And well, then we came across tinywasm, was like, whatever. It's not going to be like straight up, this is not going to be ever efficient. This is an interpreter for WASM, and putting this on the GPU is just a bad idea. But it is really interesting for testing language features, because it pretty much uses everything you could think of you're going to use in Rust, right? So if you get a tinywasm up and running, we can prove, hey, we can compile most things. And to do this, we need a bit more emulation. Like, we need recursion, we need function pointers. I won't go into detail right now. You'd rather have a big question Q&A, and we can talk about this later if you want to. But the TLDR is, yes, we can compile tinywasm to almost 90 megabytes of SPIR-V. Now, for those who need a reference, like, a typical SPIR-V binary is measured in terms of kilobytes. Maybe a few megabytes if you have a crazy shader, and maybe a few extra megabytes if you have a crap ton of debug info, like we often do if you want to include that, but not 90 megabytes of SPIR-V. So what happens if you give 19 megabytes of SPIR-V to a driver? It looks like this. A process running for 2 hours, eating 1 terabyte of memory, and going fully into swap already. And this process is not finishing. This is just the last screenshot we have of before the process crashed. It's out of memory. And we have yet to actually find a driver to run this, to like this. And we found a look at the biggest thing that's probably going to cause this is what drivers assume is that shaders are small. This is not a small shader. And what drivers also assume, because shaders are small, we can just inline everything. And once you have such a complex project as tinywasm, which has a whole bunch of indirections and stuff, and you start inlining everything, your actual shader just explodes in size. Because most shader compilers do not, in fact, support function calls, but they just inline everything, and they assume functions are just macros they can inline. Well, then it looks like this. But that's pretty much it. Thank you. If you have any questions, go ahead.
Okay, that was quite impressive. Thank you. Are there any questions here in the audience? Okay, I come to you.
So I've been following the development of Rust GPU every so often, and I've noticed I believe there was some kind of fork into the community I'm kind of wondering if that is like something that is gonna affect the future of the users, because in a way we're like how do I know that I can take this Rust code and then let's say in 1 to 5 years, whatever, I'm still not gonna like how do I say this, like be locked in into this in specific. I don't know if the question was clear, sorry.
Okay, so let me give you some context first of all. I'm a maintainer in the new fork. That fork has happened over 2 years ago. To just give some sort of timeline information. So historically what happened is basically Rust GPU was founded by basically mainly 2 companies. There was Embark Studios in Stockholm, and there was Traverse Research in Breda. They were basically both interested in Rust, and they started making Rust GPU basically. And there's also so Rust GPU is actually quite old, surprisingly. I'm not sure, it would surprise me if this repo was around already in 2018 or something like this, initially. And what pretty much happened, what you sort of hear around the back and stuff, is that at some point it was primarily developed by Embark Studios, and it was also under the Embark Studios GitHub group. And they basically cut down all of Rust funding around beginning of 22, which also affected Rust GPU, which was they were funding a bunch of projects and they were developing Rust GPU and also Cargo Deny, by the way, which they still maintain. That's the one thing they do still maintain. And Rust GPU development basically halted. It was also around the time where I started writing my master thesis. So it was perfect timing. I put up PRs and nothing happens and nobody knows what's going on. So around the summer of 22, there was a community fork, and I got basically into that, and which is why they were desperately searching for people to maintain this thing. I was just putting up a few PRs, and that's pretty much what happened. Now, going forward, I can't tell you what the future holds. I hope that now that I can commercially work on this, that we'll progress on this stuff, and there's a few more things in the pipeline I'm not going to publicly talk about. But realistically, the way Rust GPU currently works, the biggest hurdle, I guess, is that Rust GPU, due to being a compiler backend, is built upon an internal API. And this internal API is constantly changing because it's an internal API. So every Rusty version changes something, and we have to just update and continually keep updating. And that is, I guess, the biggest groundwork of Rust GPU has. It can never really be unstable. It is always unlikely, and you will always have to advance unlikely. And because it's out of tree, we're not getting the fancy changes.
Thank you.
Okay, we have any more questions? Go first.
Okay, so first of all, you're all crazy. That's amazing.
Thank you.
My question would be, you said that you can't get the allocations out, but that you mean that the data is then forever lost, or is that because of the representation is so weird? What does that entail in because there's also compute shaders. If you can't get the data out, what does that mean?
You can, so you can get raw data out. Here's your dump of the buffer, basically. So you do actually get the data out. You can't really get them out as a box. I can't just go ahead and send a box of a vec containing a vec to the CPU back and expect you to just access it. First of all, the pointer is super weird, because you have a custom pointer representation, so that's the first thing, it doesn't work. And also the pointers are 8-bit and other stuff.
Okay, and then my follow-up to that would be, can you use something like SPIR-V then on that? Or is that already emitting the wrong stuff?
Hopefully we'd have some sort of say. I always feel SPIR-V is already too high up in the stack, because there's people thinking about SPIR-V and then sending JSON to the GPU, and you're not going to do that, right? That is crazy. Parsing JSON in the GPU compute shader, holy crap. I mean, could potentially work, but what the hell are you doing? So effectively what I want to say is, I can imagine that you have just plain data structs that don't contain pointers and usize, and those you can share easily. It's just the problem that everything you alloc is difficult, because it always has to in some way contain pointers. What I could imagine if you have like buffer device address, which we currently still don't support, or arrays of descriptors, which we do support, and then build your system around that level of abstraction.
All right, here.
Yeah, you're crazy. But it's a good talk because I feel stupid. And question is, was somebody crazy enough to try integrating that into Bevy or another engine or stuff like that, so to start using it, even if it's in a very limited?
We have a few users, and I feel like most of our users are less game devy, but more like, well, there's a few people who want to do graphics, but I feel like most of the people are just like people who want to try out crazy stuff on the GPU, and are like, I can't be bothered to write this stuff in shader languages. I just want to write them in Rust. A lot of people, we do have a lot of people there. If you're building a complete custom engine, sure, go ahead. Your thing, like I've done that and it's totally doable. The bigger problem, it would be if you want to use something like Bevy. I do have Bevy up and running with Rust GPU. That's not the bigger issue. The big problem is basically Bevy has a pipeline for evaluating materials, their PBR pipeline, which is written in wgsl. And we are in Rustland, and we can't exactly just easily call wgsl from Rustland, so we somehow, well, we could maybe do something like this, but it would involve a lot of work, because we would effectively need to have a foreign function call which just survives the entire pipeline, and specifically survives the transpilation process from SPIR-V to wgsl, before it is then linked together, which doesn't exist in wgsl. That's one of the alternatives. Or you need to have some sort of process to port Bevy PBR to Rust GPU, which funnily enough, if you search for Bevy Rust GPU, we'll find a repository which is like 2-3 years, hasn't been updated yet, and it's 2-3 years old, of someone actually maintaining such a fork. So it's like, you could do it, but there's lots of barriers in the way. And I feel like if you really want to commit to like Bevy support, the easiest would probably be some sort of automatic transpilation or something like this. And at that point, you would need source-to-source code transpilation, not like to machine code you can't really read and work with easily.
Okay. Was there? Okay.
Has there been any efforts on the side of the Rust compiler to support this project?
That's a difficult question. So I feel like this project, if you're talking about like in tree versus out of tree, I feel like this project just has always been out of tree and developed out of tree to just be out of tree. There hasn't really been any effort also from our side to be like, we want to be in tree, because out of tree has the advantage we can just do whatever the heck we want. But of course, out of tree also means we need to update stuff. From like the Rust developer, I feel like most Rust developers, not to throw shade or anything, but I feel like most Rust developers want to focus on other more important things, which I can totally get. So it's like our little corner of trying to get this weird stuff up and running.
Okay.
Okay, so with NVIDIA experimenting with CUDA oxide,
CUDA oxide.
So how is the future of Rust GPU? I guess it's sort of like kind of targeted towards the shader or kind of compute both. I believe that at the current time it should be both basically. But how is that? Does that increase like competitiveness on sort? How does that work based compared to this project in a way?
I can give you like a short overview, because there's Rust GPU, and there was something before Rust GPU which turned what's written into Rust GPU, which I don't know it's exactly what the exact name was or whatever. Then next to Rust GPU, literally also in the Rust GPU GitHub group, there's Rust CUDA, which I can't really tell you the state of, honestly. There's also people developing on it, and I don't know, we're not talking much for some reason. There's Azula we wanted to talk, and they didn't join. Something happened, I don't know. But there's a few people experimenting on that, and now, and just a few months ago, NVIDIA released CUDA Oxide, which is basically, it's basically Rust to CUDA PTX compiler. So Rust CUDA and CUDA Oxide sort of try to target the same thing. They take very different paths to accomplish it. So both Rust GPU and Rust CUDA go via, well, there's Rust SPIR, which is like the medium intermediate representation in the Rust C compiler. Then they go via a library called Rusty Cochin SSA, and then they do their thing. Which is like one of the two, like there's basically two paths to get out of Mir, which is like Rusty Cochin SSA, and there's CraneLift, and there's other analysis tools, but not really for like code generation. What CUDA Oxide does, which is very weird and out there, is they go from Mir directly to their what's it called? Their NV. It's not NNVVM anymore. I can't remember exactly, but like they go from Mir directly and build their own custom backend. So in a way, it is very different from all the other approaches which we've seen. And the answer is I don't really know what's going to like be superior. Well, the one thing, of course, is CUDA Oxide is only CUDA. So that's really like the limit. Whereas this one tries to target whatever, basically. Which also means as it's only targeting CUDA, they don't have to deal with weird specs not allowing pointers. They just have pointers with address spaces.
Thank you.
But can it run Doom?
You can render Doom.
Well, you can build a render for Doom, sure, but like I have not tried to compile Doom to Rust GPU. Also, like Doom is C, so you would need to first port Doom to Rust, which is probably someone probably did that, and then you need to put it in there, and then I'm afraid you're going to get, you know, this again. And also, like Doom, I assume is going to be written to like for like a single thread context, so it also won't scale. And I mean, like this is also like single threaded, but who cares? You can't even compile it.
Okay, no more questions. As a matter of fact, I have one more question. Do you have any numbers for this? How does this perform? It's like super fast, it seems.
Define perform in terms of like Q-pointer or in terms of like in general compared to other shader languages?
Compared to other shader languages?
So compared to other shader languages, well, if we go back to like the very first slide, or like specifically to this slide, right? So what other shader languages do, they also target SPIR-V. So like without Q-pointer or anything, effectively we're just generating SPIR-V, and if the SPIR-V is equivalent, why should there be any performance detriment?
Okay.
That's sort of like the first part of the answer. The second part is, of course, with Q-pointer and some more emulation going on, you will have, in a way, a sort of higher overhead, sure. How much it actually is, we don't know, and we assume it's probably not going to be that much. And sort of the question is like, do you care if it's a slight bit more overhead or something like this? This is the next question for like the convenience of just using standard ITER API.
Okay, thank you. Please show some big respect to Sebastian. Maybe one more thing, how can persons get in contact you and your project if they have more interest in all of that?
I mean, we can talk later, otherwise I'm on GitHub, annoy me or something, there's a Rust GPU project on GitHub, make an issue, make a discussion or something. Or just talk to me later or whatever.
Okay, thanks.